So I'm Mandy Kwok, and I'm presenting my project Congruence of Solutions of Pell's equation. So what's the Pell's equation? Apparently, so it's a very famous Diophantine equation that for any positive integer d, which is not a square, we'll have this equation, and there are infinitely many pairs of integral solutions given by this formula. So by this formula, we can simplify and become this recurrence relation in homogeneous recurrence relation in order 2. And this one will be our main focus of what our congruence will be. So so we have the general formula of xn will be this form. However, the congruence of mod p, we need to question one thing first. So that is, could alpha and beta exist when we have mod p, and what would be the consequences of considering alpha and beta? So we need to divide it into 3 cases. So for the case 1, if p divides dy1 square, so the characteristic equation will have a double root in the field. So since it has double roots, the formula would in general become this. So xn will be congruent to x1 to the power n mod p for any n. So in case 2, when d is a quadratic residue mod p, so there will be solutions, and alpha and beta will be distinct. And therefore, the general formula mentioned before will still applies. So when d is a quadratic non-residue mod p, so we need to consider the field extension of the original field. And in this extension, since it's an ideal and there's no zero divisors because you can just expand it, so alpha and beta are well defined, and you can have also the same formula. So why am I obsessed with the existence of alpha and beta? Let's see. So this is the cycle mod p. That is, when we consider mod p, since there are only finitely many possible pairs of the congruences, so there must exist a cycle. And if you go back to the fourth, so you can see there must be a cycle, and there will be a minimum cycle. So if MP will be a minimum cycle, so for any cycle, for any possible cycle length, we have MP, we divide D by the division algorithm. So back to the 3 cases. When P divides dy1 square, so we know that xn congruent to 1 or negative 1. So if x1 congruent to 1, then xn will always congruent to 1 mod p. If x1 congruent to negative 1 mod p, so xn will be congruent to 1 mod p if and only if n is even. And xn will congruent to negative 1 if n is odd. When it's a quadratic residue mod p, so we have considered all the equations, we necessarily have that np will be the multiplicative order of alpha and beta mod p. Therefore, by the Fermat's-Lehto theorem, we have that np divides p minus 1. So here, let's see. That's why I'm obsessed with the field extension. So np will still be the minimum positive integer such that alpha to the power np will congruent to 1 mod p. However, in this case, since is not in the original field, so we have the relations shown here. So this implies that the multiplicative order will be divide p plus 1. And therefore, combining all the cases above, we can conclude that np will in general be the multiplicative order of alpha and beta mod p if p is not dividing d. And we can separate into 2 cases when d is a square and d is not a square mod p. And we can conclude that np divides p squared minus 1. When p congruent to 2 equals to 2, so for all even I, when it's put into subscript, xi will congruent to 1 mod 2. And when it is even, it depends. But however, they will also be of the same congruence mod 2 for when the subscript is odd. Okay, so then we are considering the cycle not the prime, the cycle will still exist. And therefore, if we let mn extend the definition, so we still have this minimum cycle to exist. However, it's not that easy to find that alpha and beta exist too. And when we consider mod prime power, so the congruence asserts that the minimum cycle is still bounded above by this. And for arbitrary positive integer n, because by the Chinese remainder theorem, we can have that the order is the least common multiple of all the functions combined together. Hence, MM is also bounded. Okay, let's go back to our original old stuff. So consider divisibility. So if there is an arbitrary odd prime dividing xd, so what does it mean? From this, we have MP would divide 4D, and MP would not divide 2D. And on the other hand, for any odd prime P such that 4 divides MP, so by the similar process referred above, so we necessarily have that if there is a P divides XD, so 4 divides MP, and for all positive integer K, P divides XK if and only if the multiplicative order MP over 4 divides K, but that over 2 does not. Okay, so since if P divides dy1 square, the sequence is never divisible by n. So we have the following. If a term xd has an odd prime divisor p, so p will also divide all the terms that is an odd multiple of the original d in the subscript. And if you compare two primes altogether, we have that 4D will be a common cycle of these two, no matter is it a minimum cycle or not. Moreover, if their minimum cycles are equal, apparently P divides xn if and only if Q divides xn. Therefore, if the least multiples of the two odd primes among the sequence are the same, that means that the minimum cycle will also be 4D for both of them. So P divides xn if and only if Q divides xn. So in the above, I actually considered only the general recurrence relations of order 2, while the roots of characteristic equation alpha and beta multiply and become congruent to 1 mod p. But in general, if this does not hold, alpha, beta may also exist, and MP will also be here, and they are also the multiplicative order of both, even if they are not multiplicative inverses of each other. And since MP, okay, so MP we also divide p squared minus 1. However, there will not be a beautiful relation between like the least multiple of the p dividing xd to the cycle. Like I actually tried to relate the cycle and the cycle length and the divisibility together before. So here, that's summary of my findings. So MP would divide p squared minus 1, and in particular, when we divide it into the three cases, we necessarily have MP equals to 1, 2, it divides p minus 1, or it divides p plus 1. Another one would be for all n, the function mn will be bounded above by n squared. Also, for all positive integer k, so yeah, we can have developed the relation between the cycle, the divisibility. Yeah, these two are actually linked together. And what is more, that if there are two primes which have similar properties when they have divide the same cycle and they divide the same least common multiple of among the sequence, so they will necessarily have the same cycle if their least common multiple in the recurrence are the same. So there is actually a minor mistake in my paper, which I just now take another road to change my presents. But yeah, anyways, this is the end of my presentation, and thank you.